Hey, everybody, and welcome to the Protocol Town Hall, a weekly guest talk series where we invite people from the field, practitioners, theorists, researchers, and teachers to come talk about important topics in the field of protocol studies. Today is a little bit different. Today is the kickoff for our technical foundations track, which will be kind of like a live coding style experience with Venkatesh Rao, one of the program directors, who's going to come on and get us started with formalizing the field of protocols and trying to do for protocols what economics did for markets in a sense, or what statistical control theory did for manufacturing. I think that establishing some foundations for which we can model protocols is going to be important. And we have events later on this year, as well as a special interest group, which will be hosted on the Discord. So I'll bring Venkat on to talk about that.
Hey, Timber. All right, let's do this thing. So I've never done this kind of Twitch-style live streaming here. So it's a little fake since there's not going to be any coding, but we'll adopt the coding style presentation. So let's see how this goes. All right, let's see where to start with. Let's actually start with the Discord, since that's where a lot of the action will be. All right. So yeah, we are trying to bootstrap a special interest group in formal models. So if you look on the left under the special interest groups category, there are three. Timber will be leading the Spannenfelding group, and he'll do a talk like this at some point to kick that off. I'm trying to get this off the ground, formal modeling, and Kia will be doing something similar with memory research. So hopefully we'll run at least 3 special interest group tracks this summer for about 6 months, and we'll see kind of how it goes. So the idea is every couple of weeks we'll do a co-working session and just do it like a study group as you might in like grad school or something. So join the Discord. The link is in the comments. I think Timber will have posted it. So you can join the Discord if you're interested in this. And we will actually, let me switch to this one. Okay. So I'm using a personal Roam graph to organize my thoughts on this track, but this is roughly what we are trying to do. So this actually kicked off a couple of weeks ago with a live workshop at Esmeralda. I'll tell you about that in a minute. And then I'm doing this talk here, but looking out for the next 6 months, I'm trying to run this as a 6-month study group with bi-weekly meetings. I'm thinking quorum of, like, besides me, 3 more people with sufficient technical ability to make the discussions interesting. So we will do things like, pick an interesting technical paper and try to read it together, maybe with some ChatGPT help if it's beyond our depth, and try to wrap our hands and minds around the challenges of formalizing protocols. Right now, I'm thinking every alternate Friday for the next 6 months. So this is what the schedule looks like. So today is Wednesday, so we'll actually kick it off this Friday. I'm calling that a warm-up session. I'll see who shows up. Timber will also post a link to a form where you can sign up for any of the special interest groups we are soliciting interest for. So Timber, if you can do that, post that form link in the comments. But yeah, Friday will be kind of the soft kickoff. Even if nobody shows up, I'll hang out on the Discord voice chat and maybe just work in public. Maybe I'll read a paper and talk out loud or something. I don't yet know what I'll do. But yeah, 2 weeks after that, June 27th, we'll do kind of a more structured kickoff meeting. Then we have, I guess, another a bunch of dates coming up. It'll probably end up going into November. But I want to point out that this track will lead into a more ambitious workshop we want to do in fall, probably in October, which we are tentatively calling Basket of Protocols. So the name is inspired by the idea of a basket of goods in economics, which is used to track the consumer price index and inflation. We think there's like something there in how we might model protocols and develop universal intuitions about them. So that's the plan. Like do a summer-long special interest groups with a few people showing up, then do this in-person event. It'll probably be somewhere in Canada, maybe Vancouver, and we'll invite a bunch of people. So if you're interested in this workshop or this whole track of thinking, you should try and attend over the summer, and especially if you have like the right kind of technical background to be a useful participant. And yeah, we'll maybe get couple of dozen people at most in person, and basically hash this out over a day or two to see what we can do. So that's the idea, the bootstrap a special interest group. Okay, let me tell you where we were the last time we talked about this. So at Edge Esmeralda, which was a pop-up city a couple of weeks ago, we did an in-person session. Maybe a dozen people showed up with various levels of background in STEM disciplines and mathematical ability. And what we basically did was just try and like get a sense of just how much formal structure is there to protocols. Should we expect it to be like fundamental physics, or is it more like anthropology or somewhere in between? And try to get a sense of that. So let's switch over to the spreadsheet that we all created together there. Let's start. Okay, you can see my spreadsheet. Okay. Timber, were you there at this session?
No, I was leading one at the same time.
Oh, okay. Yeah, you weren't there. So we had a dozen people, a couple of like strong mathematical people, bunch of people who had like college level math, and a couple of people who were like math curious but didn't have much math. But here's kind of like the frame I put on it. So this is kind of like a 2x2, more a 3x3, I guess. The y-axis is this notion called the paradigm level of a field. So that JSTOR link tells you what that is. But the idea of a paradigm level is a high paradigm field is a field like fundamental physics, where people have a huge amount of consensus and agreement on the shared foundations of the field, right? Like all theoretical physicists know about like, quantum field theory and general relativity, and they agree on a lot, right? And they have a particular culture of accepting articles for publication, how they teach. So for example, high paradigm field faculty typically don't give their students a whole lot of choice in what you must learn in order to get a degree in the subject. So you might have a few electives, but in general, to get a physics degree, you have to take the standard track of physics courses, because it's so structured and there's so much agreement, you cannot even work in physics until you get all that under your belt. So that's a high paradigm field. And on the research end, typically in a high paradigm field, researchers are quicker to like accept potentially not very important work so long as it's correct. They don't reject for reasons of like arguing that, hey, this is not important. And low paradigm field is the opposite. Huge amount of disagreement, lots of like ideological schools of thought. So, economics is somewhere in between, but something like anthropology or sociology or art history, there might be lots of different ways of viewing the field from different perspectives. Different teachers will teach it very differently. Usually there'll be a lot more student choice on how to like construct their own curriculum. And in research, you have the opposite bias. Like people might reject papers for saying, hey, this is not important. What I think is important according to my ideology, right? So that's low paradigm. So that's one axis. The other is what I'm calling relativist to absolutist. So relativist, by that I mean, it's your understanding of the subject is relative to who you are. So that doesn't mean it's subjective. It's not like, I like vanilla ice cream and you like chocolate. It's more like how you view things depends on like the perspective you're viewing it from, right? So in anthropology, whether you're an insider or outsider, that's called emic versus etic ways of looking at a society. That's your understanding is relative to who you are, right? So that's relativist. Absolutist is, stuff like number theory. It doesn't matter where you came from, what race or whatever you are, the theorem is going to be true for you. So it's kind of absolutist in that sense. It doesn't matter where you come at it from, something like that. I know there's a lot of controversy about this and discussions in the postmodernist vein about this, but there's a loose distinction. And we had a big brainstorm about where does protocols land. So we came up with these 9 categories, and most people kind of agreed that it's somewhere towards the center, maybe even going down to the bottom. But the challenge we want to set ourselves in the special interest group is to see how far, if we push ourselves, we can get towards, absolutist and high paradigm? Can we actually make it look more like math or grand unified theory? So we spent some time doing this, and we did it in a couple of different ways. Let's see, what else to look at? I won't look at that. Okay, so we did a bunch of like calibration conversations relative to other fields. I'll say more about this when I go back to my Rome page. But yeah, we compared this to economics, aerospace engineering, architecture, various other fields like that, right? And we talked about like, how do these fields actually integrate themselves? So physics, for example, has a grand unified theory. Or sorry, math has like I would call it grand unified theory in the sense of like mathematicians like Grothendieck who try to systematize all of math. Physics, even though the phrase grand unified theory comes from physics, it's not really quite grand unified theory because there's a lot of like epistemology and ontology that creates like a slightly more contentious structure. So for example, people may or may not agree that superstring theory is valid knowledge, right? So anyway, we did a lot of such comparisons. What else did we do? We populated this huge matrix of looking at what we call a basket of protocols, which I mentioned will kind of be the theme of our fall workshop. So on the columns are a whole bunch of protocols we want to potentially include in the basket for considering. Like, if you try to do formal modeling of protocols, it's useless if you can only model one protocol. So the challenge is, can you model several very different looking protocols on the surface with nothing in common? Can you share them, unify them within the same modeling framework, right? So Ethereum is the technology that's sponsoring this whole program, so that might be one. But talk about royal court protocols, how you go and approach an emperor. Or is there anything in common? Would a formal model capture that, right? So that's the columns. And then the rows are kind of the important attributes of phenomenology that are probably important to include in the formalism. So for example, protocols seem to have a temporal characteristic. They unfold in time. People make commitments in time. They disagree and have incentives that pay off or not in time. So temporality is a feature. Commitment is a feature. Memory is an important feature. Some of our most important conversations over 3 years have been about how does memory interact with protocols? And this can be both traditions and rituals type memory, or memory in the sense of the Ethereum blockchain has like a historical memory on a ledger, or it could be like a standard like USB has a path dependent history coming from various connector cables in the past, right? So memory is a very important part of how protocols are defined and emerge, and related to that is evolution, which Timber had the research paper in our first year looking at the evolution of safety protocols in coal mining. So protocols have evolutionary characteristics. So that's also probably important to model. So I started with some columns and some rows and filled it out, but we had like a dozen people in the room filling this out. So we had a whole bunch here. So this is raw material for us to work with. And then we tried to ask like, what kinds of problems, questions, and mysteries should protocol studies study, right? So this one, how do you ossify a protocol in a controlled way, is a question that motivated this program from the Ethereum perspective. And this is the classic decentralization question. How do you define whether a protocol is efficacious or successful in a relatively objective technical sense, right? And we were trying to compare with similar questions in other related fields. Okay, so that's what we did a couple of weeks ago. So that's where we are now. So going back, let's go back to the room. Okay, let's get into this talk. Okay, so this is a working in public live co-working session. So this is my initial brain dump. Normally I would do this in a paper notebook or a whiteboard, but I couldn't get a whiteboard type setup going in time. So we are doing this on Rome. But yeah, I'll edit it as we talk. Right. There'll be some math theater, as in I'll like flash some math on the screen, but we won't really get into it, at least in this session. In the special interest group sessions, we may do that a little. Math calibration level. So this is important. So this is for the summer SIG. I really think of this as there's this phrase street fighting mathematics, and there's a MIT open course about it and a book. So let me actually show those. So This is the course, Open Courseware, Street Fighting Mathematics. It's taught by Sanjay Mahajan, who's also the author of the book. It basically takes the kind of mathematics Enrico Fermi was really famous for, right? Very quick back of the envelope, paper napkin type calculations to estimate really complicated and like sophisticated stuff, like the yield of a nuclear explosion. So that's called Fermi estimation. And that's the broad philosophy of this course that this guy teaches at MIT. And I think he's actually at Princeton, though the course is on MIT. But let me share this other one. So I highly recommend this book, which I have by Mahajan, called The Art of Insight in Science and Engineering. So this is like usually high school or low undergrad level of math. Often it's just very quick arithmetic and things like that, but you can get surprisingly far with really complicated questions just doing this kind of back of the envelope math. And this is kind of the level of technical sophistication I want to calibrate. So I think the way to think of this is you want to have good technical taste and a good deal of maybe technical experience in some narrow sense. But what you want to do is work at the level of like technical intuitions and strategy. But the difference, going back to my talk template, is I hope this is like easily visible for you guys. I'll increase the size a little bit.
That's better. Yeah.
Okay. So I'm calling this very similar to that street fighting mathematics level, but for formal modeling and design rather than, quantitative estimation. So we are not going to be doing things like, how high can a mountain get or how much energy does a nuclear explosion release. We'll be doing more things like, here's the TSA checkout or TSA security process, and a bunch of people are doing a bunch of things with metal detectors and X-ray machines, and people are getting mad and annoyed. How do you represent this mathematically? What are the atomic units? Would you represent this as a graph or a Gantt chart? What would you do to represent it? What statements can you make about that formal representation? What properties can you infer? Can you like prove theorems about that representation? Can you say, for example, in a mathematical sense, that the American TSA security protocol is worse or better than the protocols at Tel Aviv airport in Israel, right, which is a very conflict-prone area, and I think is famous in airport security. So that's the kind of stuff we want to be doing in this formalization track. And this is going to be a little meta since we're trying to set this up, but the actual special interest groups will, of course, be more collaborative. It won't be just me talking and occasionally like asking Timber a question. It'll be more like all of us talking, and it'll get into the actual specifics. So we'll pick out something interesting to talk about, like maybe a paper, and try and read it together for a bit and then discuss, maybe use ChatGPT, plug the paper into ChatGPT and like do something with it. Maybe we'll do like a co-working session where we say, hey, maybe graph theory is the right way to model protocols, and let's pick 3 sample protocols and each of us go off for an hour and try to like model it at graph theory, and we come back and share and compare notes, right? So that's the kind of like idea I have for the special interest group. Okay, so why are we interested in doing this at all? So those of you who've heard me do summer protocols talks in the past have heard like, I don't know, 10 versions of this, but I just want to set up motivation that this is not random bunny trail of nerdy interest that's of no relevance to anybody. This is actually an important topic for the world. So these graphs I like to show kind of like illustrate why. Use of the word protocol, it kind of really exploded after around 1975 or so, really went up. And this is, of course, with technology becoming a much bigger part of our life. It peaked around 2000 when internet protocols were a huge topic of discussion. Then it went down to a small plateau. And if you look at that last bit, may not be clear, but you can see a small uptick. That's when interest in blockchain protocols exploded, and also, things like Blue Sky and other things. I won't belabor this, but the use of the word protocol has really exploded in TV shows, and I have a whole talk about how that is revealed in Doctor Who and Star Trek. So this might not be like deep evidence that something like a deep planetary scale trend is going on, but I think it's very suggestive that we use the protocol so much to talk about our world and tell stories about our world. And this is the really fun one that really got me thinking about this, that this is a huge planet level trend. It's a video that one of our researchers in the first year made that just is a series of clips from movies where people are using the word protocol. So it's a lot of fun. I won't try to play it, but it's a lot of fun to get a sense of like the rich context behind the Google trend of protocols becoming a planet scale thing. So the TLDR of the motivation is the world really is getting super protocolized. It's like very invisible. It's almost like a technological version of climate change. It's invisibly happening around us. And most of us haven't noticed that the world of today compared to the world of 100 years ago looks much more like a really complicated multi-stack machine that's full of protocols that operate in machine-like ways. And we all are embedded in this kind of like techno cyber matrix, and we almost don't realize it. So the idea is to start studying it and making sense of this reality we are in. So that's the motivation. What's the big qualitative thesis behind this formalization track? That protocolization is one of the big TION ending words, right? Like globalization, industrialization, urbanization, modernization. I think of these phenomena as full stack planetary transformation. So something like a terraforming, right? But there's something interesting about this one compared to the other ones. The other ones were mostly, I would say, social, cultural, maybe a little bit economics has a little bit of a technical edge to it. But what's happening now, because it's being driven by computers and the way computers are organizing the environment around us using like very hard-edged things, this almost looks like we are creating a mathematically defined hyper object, right? Like when you say study modernization in the Renaissance, it's a lot of like very cultural things happening, even though there's some technology involved, the printing press, which we're studying now, by the way. But it's fundamentally a social and humanities type phenomenon, right? The Renaissance and Reformation. What's happening now is that we are becoming transhumanist at almost a species level. We are becoming part of like a big connected machine, and we are all parts of that machine. So it should be possible to study it in more of a STEM idiom, right? So the idiom shouldn't necessarily be like, humanities. We should be able to study it the way we take apart and study a car engine. We should be able to take apart this planetary protocolization and ask, how does it work? What are the moving parts? What's the grammar and hard-edged rules that allow it to function, right? And people even use such language, right? When they talk about geopolitics, they use the phrase rules-based international order. Rules-based, that's kind of how you describe machines, right? And it's breaking down now, but what's coming in place also is a new kind of machine. There's a grammar to it, right? So there's a big leap in the last 50 years, and this is highly under-theorized, especially in a more formal sense. There are, of course, social scientists who write a lot about it, political scientists who write a lot about it, but they do so in humanities and social science modes. And I think this is understudied in a technical way. The cybernetics people did a little bit. I'm not super happy with that approach, but I'll talk more about that in a bit. Okay, what are the kinds of goals a formalization effort could have? Immediate goal is, of course, bootstrapping the SIG. Medium term is to like converge in a workshop in 6 months and like over 24 to 48 hours, really set the agenda of what can we do with formalization of protocols. Long term, and long term for me in this program is 18 months. Can we develop a set of initial working papers that are at least good enough to maybe do like an edited collection, the Springer type of collection, and suitable for seeding more serious research, get people doing grants, maybe even PhDs, who knows? So this talk, I want to give a sense of like what is possible, calibrate against historical precedents, things like that, okay? All right, goals make sense, Timber? Are they kind of clear?
Yeah, I think so. And yeah, every other piece of like cross-subject protocol studies that I've seen is very social sciencey, if not completely artistic. And I haven't seen anybody try and do like logic or math or like rigorous formalization of this stuff. So
yeah,
it is a completely new field for people to run with, which is cool.
And that's super exciting. And I mean, there is technical work, but it's super narrow. You talk to Ethereum people, they model their stuff technically in very narrow ways. You talk to networking people, and that's very close. It's still computing technology, but TCP/IP networking people kind of have their own little silo world that cannot even talk to the Ethereum world very clearly. So even that bridging is hard, let alone broad foundations extending all the way to climate change or something. Okay, I want to quickly share a couple of definitions for those who are completely new to this conversation. So we're going to be talking about two kinds of protocols. A macro protocol is what we call an engineered argument. So think of a decentralized network of agents that might have different incentives and are interacting through, say, a blockchain or a network of computers or a bunch of countries arguing with each other about a climate protocol. So that's kind of macro in the same sense as macroeconomics. And micro is a behavior designed for reliable repeatability. So there's a definition I just made up last week. Macro definition has been around for a year for us. And this would be an example, would be hand washing. So let's take a quick look at what formalizing thinking about protocols might look like. So let's do a simple example of hand washing, right? So look at how hand washing evolved in our world. So there would be some time in antiquity, I guess somebody noticed at some point that if you wash your hands before eating, you don't fall sick as often, right? But there's nothing more formal than that. Maybe grandmothers are telling their grandchildren to do that. Then usually there's a religious codification, which is a kind of formalization, but there's no rational rigor behind it. It's just codification of intuition and anecdotal experience. So for example, in Islamic culture, you're supposed to do ablutions, I think, several times a day in a prescribed ceremonial way, right? So that's a hygiene practice, but it's grounded in religious justifications rather than a scientific understanding of why washing your hands is a good thing. Then you get to things like pre-formal empiricism. At some point, presumably somebody noticed that washing with soap is more effective than washing with just water, right? Then you do formal empiricism. Somebody notices that if you do it systematically in a hospital, the mortality in hospitals goes down by X%. So this would be, people like, was it Pasteur who saw this first? Or, Louis Pasteur, I think. And then Florence Nightingale applied it in the Crimean War, right? And then you get the first theorized model. So this would be, Pasteur had his germ theory of disease, I think, and Joseph Lister started protocolizing the practice in hospitals. And there's an interesting story here that shed some gender light on it. So the research showed that surgical outcomes were much better when surgeons washed their hands, but because surgeons were typically all male then, and nurses and midwives were women, they were more arrogant about it. So the practice actually didn't get adopted. So the mortality rate for young mothers and infants actually went back up, but the rates improved for midwife and nurse assisted births, right? So this is a weird little anecdote that shows you how protocolization can connect a very technical field with very mathematizable stuff with very social and cultural things. But okay. At some point, the formal empiricism goes to a theorized model, which is very local and specific. Somebody does research on how bacterial cell walls break down and comes up with actual biological models of why so many microbes get killed by hand washing for so many seconds. Maybe they draw curves of percentages and stuff. And then at some point, all this academic theory comes back into public life, and somebody comes up with the clever idea that the way to install this behavior at scale is to do something really simple, like teach people that you should wash your hands for as long as it takes to sing happy birthday, right? So that's as much as protocols evolve in a very narrow sense. And usually they end up with a terminal tension where they've improved as much as they can, and you're actually running into trade-offs of doing more than that, right? So for example, now people argue about especially if you use hand sanitizer too much, maybe you're actually lowering immune effectiveness and helping resistant strains of bacteria emerge. So there are people who argue that you shouldn't wash your hands so much, right? So this is the almost prequel to formalization. This is the pre-formal or pre-general formalism history of a protocol. But okay, ask yourself how you might actually formalize this in a generalizable way. So the way to do it that's not very interesting is modeling the specifics of hand washing in increasing detail, right? You could like come up with extremely detailed models of like species of bacteria and how long it takes. You can like compare kill percentages versus time for ultraviolet radiation versus soap versus alcohol. You can do all of these things, right? And all of them might be useful for places where you need to get super specialized, like hospital, for example. But what we want to do is actually do what I think of as horizontal generalization, which is, can you generalize in ways that apply to other protocols? So we are still micro protocols, by the way. So here, for example, this is how I would do it. This is my taste in technical modeling and how I used to do it back when I was doing like technical research. Start by defining a class of interest, right? In this case, it is situated agents that serially exchange mass and energy with multiple adjacent systems, including mass energy transfer. So this, I'm just reading that out, but think about what I'm trying to say here, which is I'm a human being. I go through life, typing on my computer, then going to the bathroom, then cooking in my kitchen and eating, then going down to my car and driving somewhere, shopping, shoving a shopping cart. So I'm moving through a series of situations in which I'm situated. So this is, by the way, a term of art in a lot of computer science. So when people say situated, they mean typically this, that you're like somehow in a feedback loop with the environment. And as you're doing that, you're of course establishing boundary contact with your environment. So I'm touching faucets, I'm touching various orifices in the body, I'm touching a laptop keyboard, I'm touching food preparation materials and food itself, I'm touching the handles of shopping carts and steering wheels, right? Lots and lots of contact, and mass and energy and live microbes can go back and forth across a boundary. That's the class I'm interested in. Then I formalize. Maybe I say that the way to describe the behavior of this agent is as a finite automaton. So for those of you who don't know, that's just a machine that cycles through a bunch of states, like your washing machine. So it's like an automaton cycling through action states, which could be classified or tagged semantically. So washing machine might be something like, filling, washing, rinsing, spinning, drying. So similarly, you could have behaviors like, I'm touching a steering wheel, so I'm contaminating, or I'm touching a poison, so I'm literally doing unsafe material transfer. So I can classify all these behaviors semantically and sort of like create a vocabulary. Then I might model the actions at an atomic level and add sanitization behavior in the instruction set. So washing hands is a sanitization behavior, right? And then I might introduce a grammar rule and say, certain strings validate correctly if the behavior described by them has the atomic item for sanitation every second item, right? So that's one way to do it. So this is like creating a grammar of the sort DNA has for DNA molecules. Okay, so now we've kind of like set up a representation formalism, and we can do things like characterizing the difference between hand washing and non-hand washing in various terms. So wash after every activity, wash twice a day, wash only when you go to the bathroom. And then you can keep adding this to the model of like how you transition from safe to unsafe behaviors, right? And then you can model the bad protocols as being those behaviors that are more liable to fall into bad states, like, unsafe. Like maybe a transition sequence from working in your garden to eating food is a sequence that's unsafe, and the probability of becoming sick increases by X%, something like that. So now we've done kind of a horizontal generalization, and this can extend to other behaviors. You don't have to like just go and model bacteria in detail in a hospital context. You can do things like, does this apply to handling acids or industrial chemicals? Can you substitute wearing gloves for washing your hands? It's a different prophylactic behavior, right? Does this generalize to touching hot objects, which is a different kind of safety exposure? And then you try to theorize a mathematical class around this, where you say, I'm going to call this class of systems prophylactically stabilizable systems, or PSS, and I'm going to start making propositions and proving theorems about this. So this is roughly how people in my home discipline of systems and control theory approach problems of modeling and formalization. But the interesting thing that happens as you go through this process is you've almost weaned yourself from the motivating, very practical case to a mathematically interesting class that you're handling because it has mathematically interesting properties. So at this point, you've kind of like almost cut yourself off from hand washing as the motivation and say, hey, I'm studying this because it has certain interesting, very tractable properties. Like maybe it's a linear system, and because it's linear, I can do a lot more with it. And therefore, I'm going to study linear PSS systems and then come up with a whole bunch of general recipes for making such systems safe. And then I can go around and say, does any particular practical system meet particular necessary and sufficient conditions? And then can I somehow push a button and safe practices from hand washing in bacterially contaminated environments suddenly lead to very clever protocols for a different kind of unsafe environment, right? And even if you don't have such practical transfer, this kind of elegant formalization is usually interesting to study in its own right and has all sorts of interesting dividends. So this is a simple example of how you would formalize from a practical starting point. Let's do a little bit more complex example. So this is actually old postdoctoral research I did in 2004 to 2006 that I'm dusting off and refamiliarizing myself with. My technical skills have gotten way rustier, and I couldn't do this now if I tried. But it's a good example of a macro protocol, which is, at the engineered argument level. So let me switch over and show you what that paper is. So if you're interested in this, it's in the IEEE Explore. It was published in the IEEE Transactions on Systems, Cybernetics, and Man, Part B, which tends to publish cybernetics papers. And the problem was creating simulation models of entire battlefields with UAVs, robots, human soldiers, human commanders, AVAX aircraft, and an adversary trying to win against you. So that was the context. It was the Air Force project funding my postdoctoral research. And this was what I developed as my work on it. Let me switch over to the paper I did, which I think I can retcon as this is formal protocol theory, because a lot of what it was actually about was protocols. So this is the paper. Let's see if I can increase this. Timber, is this kind of readable?
Yeah, that looks good.
Okay. So there's a bunch of math in it that I'll flash at you, but this is kind of what I ended up building, which was what's called a battle space modeling environment. But this one was a prototype I built entirely in MATLAB, but there are real production versions of this. So the Pentagon has a bunch of software like this that support what's called shared situation awareness. So commanders in a battle theater or war theater, they have views like this showing, where different assets are, what missions are underway, and so forth. So this was me developing a formal theory of how to model battle spaces, how to represent them using dashboard and command and control systems. So this is what I built. Let's see if I can maybe walk you through. So the basic intuition is very simple, even though the mathematics is not. So when a lot of robots and humans are moving around in a space, they're like physical objects that can collide, right? And often what happens when you're modeling such physical mobile agent systems is you get bogged down at the level of obstacle avoidance, where you spend all your brain power trying to figure out how to not run into each other. And that tends to bog down how you think about the larger system. So I came up with this idea that you can represent things with tolerance zones around them. So that's what the patch in patch models is. So if you have a team of a SEAL team of 5 soldiers going towards something they're trying to attack, you might draw a large polygon around them and say that's where they are. Now you don't have to worry about how exactly are they getting around this tree or gate or whatever. You just assume that these patches can move through each other and don't worry about that. That's a detail to be worked out at the detail level. So that means that these patches can overlap, and there's a grammar to how they overlap and interact. One can be inside the other. So if the SEAL team gets inside the enemy camp, one polygon will be inside another polygon, right? So that's the spatial version. And then on the right, you can see what I'm calling the trace view. This is a similar one as a similar view of time, which is it takes you like maybe an hour to go from one point to another, and at that point somebody else is doing something else, so the two time intervals might relate in some way. One might be inside another, one might be overlapping. So this can be modeled using something called the temporal interval calculus, and the spatial stuff can be modeled using something called region connection calculus, RCC and TIC. So these are formalisms that were developed in what's called the qualitative spatial reasoning community. This was a subfield within classical old-fashioned AI. So I use them to represent stuff happening in battlefields. Okay, and I wrote this paper about it. Let me show you a few more things. So there's a lot of detail about how this is set up. Here's some very rough math. So for those of you who have done any control theory systems theory, this is basic differential equations with some observability and controllability stuff going on. It's modeled in a discrete way and so forth, usually. It's a vector matrix kind of stuff. There's a bunch of entities. I can show you this math too. So all that stuff, polygons and stuff, you can set it up as like a very clean model that can be simulated by a computer. So this is like a matrix model of all that. There's a hierarchy of stuff going on. You can see for in this picture over here, you've got decision makers at various nodes. They each have different views of the situation. They're each building mental models of what the situation is like, which may not agree, right? And then they each have like representations in dispatch formalism. And that's like the hierarchy of like decision architecture with which they make decisions, and then they interact and things happen. So that's kind of the setup. So there's a lot more you can do here. Let's see if there's anything else interesting to point out here. So all this is a setup for, no, this is interesting to watch. This is the RCC8 representation vocabulary. So DC means disconnected from, EC means externally connected, PO means partially overlapping, TPP I think means one is inside the other. I forget what exactly it stands for. This was all 20 years ago work. But this is like a set of 8 primitives, which actually can be modeled in a very mathematically rigorous way. So I think they end up forming a T3 topological space, as mathematicians call it. But here's an example of what a simulation looks like. And yeah, what are different models doing? Who's making what decisions? This is kind of like the kind of chart you might see mapping industrial processes, right? What else is worth showing here? Let's see. Oh, this is a state machine kind of representation of things happening. This is what I meant by patches being abstraction. So you might be modeling something like a Humvee moving along a trajectory, and it has to do various obstacle avoidance things while it's doing it. And it might have to like, take into account steering constraints and like figure out detailed trajectories the vehicle can actually do. But it would be stupid if the general commanding the army sitting in like, CENTCOM in Qatar is, so this was in the context of the Iraq war, if that person has to worry about how the vehicle is turning, right? You want to give that person a representation that's abstract enough to make sense for them. And in this case, it would be just this team is over there and is moving over there. That's the level the general needs to look at. Let's see, what else is here? This is, I'm just trying to give you, so I simulated a whole mission. This was kind of the simulation point of like a team attacking an enemy camp, something like that. This is another interesting thing to look at. This is the vocabulary I came up with for representing what's going on. So it's like a language in its own right for describing how these models evolve. And using that, you can like formally describe what's happening in the mission, right? So this is an example of like something you might see in a video game or in a real war, a team attacking a camp and so forth. But all this can be completely formally represented and simulated in the system I built. Now, this is intimidating. I don't think I could do this now. This is the history of what happened. There's one more thing I wanted to show. All right, I won't spend more time on this. This should be enough to give you a sense of what I mean by formalizing a protocol. And this is still, though, I would say, kind of vertical. This is useful for modeling battlefields. Maybe it's useful for modeling traffic systems in cities. Maybe it's useful for modeling a disaster area where earthquake rescue operations are happening. But it won't generalize to say, how do you negotiate climate treaties, right? So it's general, but not that general. I wouldn't know how to apply my formalism to climate treaties, because climate treaties happen in not physical space and time, but in like a conceptual space of like carbon emissions and so forth. But you get the idea. What do you mean by formalizing? It's this sort of thing. So that's my complex example. This is from the brainstorm that we did on in Esmeralda. What are the types of things you might want to model, right? Time is a big one. I'm really interested in time, and I think time plays a big role in protocols. Memory is another one, incentives, behaviors. You get the idea. So
how much does like finding an appropriate unit of measurement fit into this? Like, because many other formalizations like have units.
I think that's a huge thing. If you find the right unit, it really can crack open a problem. So to give you an example, back when I was doing this work that I described, a big problem was people arguing about, oh, how much does this automate work, right? So there was the big Air Force imperative was, we want to like take away the dull, dirty, and dangerous work from humans and give it to robots. So that was the phrase used at like general level conversation. Dull, dirty, and dangerous. But what does that even mean? How do you know how much work a machine is doing versus how much work the human is doing? So some weird counterintuitive things. In running unmanned vehicle operations, so Predator or Global Hawk type drones, it was interesting. I think this was a factoid about the Global Hawk drone. It turned out that to support an F-16 class fighter, you needed maybe 22 ground staff, versus something like 50 for Global Hawk, I believe. I may be forgetting the exact details, but this kind of like is ironic, because you're claiming that automation actually should take humans out of the work, right? So now you have more humans supporting a single mission than you did before when you had a human pilot. So I was looking at stuff like that, and I was wondering, this is the wrong level of granularity to be talking about human-machine ratios. So I came up with a measurement that was based on the instruction set, like individual actions and the behaviors. And I started measuring in the simulation how many actions or decisions were taken by the human versus how many actions and decisions were taken by the machine. And this I measured at the level of that grammar or command vocabulary I was using to describe the system. So that gave me a much more useful measure. And this is also useful because at that level, you can say this behavior is dull, or it's dangerous, or it's dirty, and therefore the rate of it being done by a human is much higher. And if this is done by a machine instead, the value goes up. So it gives you very fine-grained control over like measuring what you're actually measuring, and not even measuring, like just modeling it even, right? So yeah, super important. Often finding the right units, or not unit, but the right objects to model, like it's like unit economics and business models. This is kind of like ontological economics. What are the right primitive entities to work with? Yeah. So I'll give you, okay, these are the basket of protocols from the spreadsheet I showed earlier. What else do we have? I don't want to. So there is a question of like, can what we're trying to do, can it actually be done in existing fields? Like, is this a game theory problem? Is this a science and technology studies problem? So short answer, I've thought about this a lot, not just in the last couple of years. This is a personal interest. Thought about it for 20 years. I think the answer is no. The kinds of things we're trying to do here cannot be formalized in existing fields, whether formal in the mathematical sense or even a social science sense. I want to like quickly show you guys how I'm thinking about the meta of this. So I started making this table of how does formalization actually happen in any field. And I came up with this multi-phase idea. So the columns are different fields I want to compare historically, and the rows are different. Let me make this smaller. So take, for example, classical mechanics, which is a highly formalized field, right? Starts with physicists like Archimedes coming up with like principles like buoyancy way back, but these are like isolated bits of knowledge. Then you kind of have what I think of the quasi-bullshit phase, and a lot of stuff that happened during the Arab science era was this sort. There was some empiricism, some formal rigorous theorizing, but also a lot of mixing with like magic and that kind of like irrational ways of thinking, and so it's all mixed up. So you see that in the Middle Ages a lot, mostly in the Arab world. Europe was not yet catching up. Asia was like kind of out of this picture. Then usually you have like a pre-paradigm empiricism, and in mechanics that would be Galilean mechanics. He didn't have super clear ideas about mass and velocity and things like that, but he was getting it way righter than Aristotle, for example. So Aristotle I would call quasi bullshit physics. Then you have the beginnings of formal sort of like contours. So Descartes, I think, was the first one. Not only did he come up with a lot of the math required for classical mechanics, so what we now know as analytical or coordinate geometry, where you represent geometry using algebra, he came up with that. But he also had a lot to say about what is mass, what is velocity, things like that. And then what we would call the early paradigm. So the Newton's laws you learn in physics, which also Christian Huygens and Leibniz, of course, contributed to 1680s. Then you have what I think of as the paradigm scaling phase, which you wouldn't have seen if you've not done beyond high school physics. But when you learn things like Lagrangian physics, where you don't have to do as much like almost like clever math to solve problems, it almost like plug and play formulas. Lagrangian ways of doing dynamics are kind of plug and play, still requires some skill to do it, but Lagrange starts to automate the process. By the time you get to paradigm maturity, where I would put Hamilton, it's starting to get really automated. This is almost at the point where computers can do classical mechanics for you. And at some point, the entire paradigm gets automated. So this actually happened for classical mechanics as late as the 1960s. So anytime you use a CAD software for doing engineering today, so, I use, what's the one I use? Oh man, I'm blanking on it. But any CAD tool you use, it's under the hood, it has an engine running on Keynes equations, which are like a 10-generation descendant of Newton, but it can be represented in a form that computers can just automate most of it. So you have similar things happening in chemistry. Democritus was the first kind of like beginnings of like prescient guesswork at atomic theory. Then you have alchemy. Then you have Lavoisier starting the pre-empiricism. At some point, I would say formalization started happening when Berzelius, who's not a very well-known chemist, he came up with the modern system of writing chemical formulas and equations, which is a hugely important step. When you can get to that step, you've probably turned something that looks more like a humanities or social science or like magical thinking, and turned it into something you can do much more formal manipulations with and start to make credible truth statements about. Then, of course, you have the periodic table, which was a big formalization. At some point, you had the Bohr atom, which is kind of the end of chemistry as an independent discipline, because at that point, the foundations of chemistry bleed into physics. But chemistry itself at that level, it turns into an automated engineering field. So it's not as far advanced as physics, but there are CAD tools that kind of automate all the chemical formula thinking. I just learned about this from ChatGPT yesterday. There's something called stoichiometric matrix methods that are used in the equivalent of CAD tooling for chemistry, right? And similarly, I think protocol formalization is probably going to end up looking like economics. So we should probably calibrate against that. But here I would say, yeah, in the beginning, it looks very much like social science. So if you look at like, the Aristotle's Politics, or in India, you had Chanakya, who was in the same 300 BC era, their treatises look like advice to emperors, right? Aristotle famously was the advisor to Alexander. Chanakya was the advisor to Chandragupta, the founder of the Mauryan Empire. So you had basically things that look like political science. Then you have Ibn Khaldun, who comes up with the first beginnings of guesswork of maybe there's some lawful behavior here. Maybe when prices go up and down, there's something more happening than just a bad emperor messing things up, right? Then you start to see formalization in Europe. William Petty, I had never heard of him before. He apparently was the first to start thinking systematically. Cantillon, I've heard of. All the blockchain people have as well. When you increase money supply, it's called the Cantillon effect for how that enters the economy. So that's 1730s. I didn't know that he was before Adam Smith. But Adam Smith, I would say, is the early paradigm. By the time you get to paradigm scaling, I think the important step is Walras. So Walras is the guy who came up with the general equilibrium theory, talking about how markets create equilibrium. Now you're starting to sound like physics, right? And then at paradigm maturity, you have like central banks coming up. You have overall theorists like Keynes and Hayek who come up with schools of thought. So this is a low paradigm field compared to physics, for example. But by the time you get to like, von Neumann and Morgenstern and John Nash and the game theoretic foundations, you can now actually literally simulate entire huge economies. So big economic modeling outfits, they literally do this. They're not working with toys. They're actually working on modeling the entire US economy and trying to make predictions based on it, right? So this is how I think formalization happens. How much time do I have? I have 6 minutes, so I'll keep going here. So that's the trajectory of formalization. Oh, okay. I do want to like show. So the ones I showed kind of have like a classical mode of field development where it ends up with like mathematizable formalisms that can even be turned into computer software. But I wanted to at least use one thing from the more postmodern end. So this is the development of what we think of today as science and technology studies, which is kind of like an applied sociology / anthropology, but within technology infrastructures. So ChatGPT came up with this timeline that maybe the right starting point is Karl Popper's theories of science. You get to like Thomas Kuhn's ideas of paradigm shifts and revolutions, but it starts to look like a field in its own right when Bruno Latour came up with actor network theory, which is how does science actually unfold in society? It's a network of actors and entities and so forth. And then you build up from there. A couple I want to point out that are going on right now are Timothy Morton's hyper objects, Benjamin Bratton's Stack. These are like modern ways of thinking about science and technology. And there's a lot more. A lot of it looks very much closer to the anthropology end, but some of it starts to look like, hey, you could put this in a mathematical model, simulate it, and turn it into a video game, for example, like Civ or Minecraft or anything. So I think video games are actually a very interesting class of systems to think about when we think about formalizing protocols. Like maybe the right way to do protocol formalization is to come up with a video game engine for protocol video games that would look something like what's that, the Kerbal Space Program, right? Kerbal Space Program is when you can run an entire fairly realistic space program. There's the game for doing factory automation. What is that? Factorio, I think. So these are all kind of narrow game style models of like protocolized environments, but maybe we can come up with a protocol game engine. Maybe that's the thing a formalization effort should aim at, right? What else do I want to talk about? Benchmarking, like I already said, on the spectrum, I think we're somewhere near economics, but maybe we can get to grander, more unified theory than that. All right, I think it's important to like keep sight of like what are the actual practical questions we are trying to work on. And I think, let me see if I can, why is this not expanding? Oh, there we go. Okay. Since we are like using economics as an analogy, I would say macro protocol theory is kind of like macroeconomics, where you're using the engineered arguments definition, where there are lots of agents with different objectives in tension. So what Timber is going to be working on, which is tension field theory, would be like one approach to practically working on these problems. But the kinds of practical questions you might ask are, which of two countries is more likely to renege on commitments in a climate treaty? Is this peace treaty between Ukraine and Russia going to hold or break down? Things like that are what you might study in macro protocol theory, right? And we have one promising approach, which is the Spanningsfeld approach that hopefully Timber will make a breakthrough on, along with whoever joins him in that study group. And then micro protocol theory, this is what I'm defining as reliably repeatable actions using things that look kind of like recipes or playbook plays, right? So you can ask things like, here you're almost doing things like designing software architecture. So you might say, given the goals of a protocol, so for example, case law in the judicial system where judges put down decisions and they're recorded in volumes that accumulated like a huge history of decisions that future judges refer to. This is a system with a growing pile of memory. So you can ask, how much memory should it have? How should it be factored into the current state? How should it apply to future decisions? This is a computer architecture type question, but it's not a computer, right? The judicial system is kind of a human-like computer, but it's not a computer. A blockchain is like, code is law, is a way of thinking about this that bridges the world of law and the world of computers. So a blockchain is this, but similar kind of memory questions. Uh, Unconsciousness. So this is something we've talked about a lot in the program, where we use the definition from Whitehead, which is civilization advances through the number of operations we can do without thinking about them. So automation is the payoff of good protocols, and the danger of bad protocols, I guess. But lots of features are involved in things getting automated and unconscious, right? So overrides, kill switches, human in the loop, alertness management, all these fit in. So an example I like to think about a lot is the Air France crash more than a decade ago at this point, which was two junior pilots with the senior captain asleep off shift below deck, and the pitot tube, which is the instrument that measures airspeed and pressure using pressure, it iced up. So ice kind of like froze it, and that confused the autopilot. So even though it was good weather and the plane was flying level, the autopilot was going crazy and thinking it was like in an uncontrolled dive. And the two pilots on deck, because I think it was night and the visibility wasn't clear, they were panicking and they were trying to like fight with each other, and the plane crashed, and the senior pilot who could potentially have resolved it was asleep, right? So this is autopilots, humans in the loop with different levels of training, different parts of the training curve. How do you model such things? If I gave you a random such protocol in a nuclear reactor or an AI system that's making critical decisions, could you analyze it and say this is too unconscious or not unconscious enough? Could you do that, right? All right. And since this program is funded by the Ethereum Foundation, there's a lot of Ethereum specific questions that we are, of course, interested in. So one that keeps coming up is a big value or core principle of the Ethereum infrastructure is censorship resistance, which is a political value, right? But how does that translate to very detailed level things that are discussed in Ethereum protocol changes? So for example, people talking about the Ethereum object format or blob sizes in L2 chains. These are very detailed technical things, and it's not always clear how does this actually affect high level values that you're trying to solve for, like censorship resistance. Could you model the protocol in a way where you can plug in an EIP, which is an Ethereum improvement protocol proposal, and say, does this increase or decrease censorship resistance? Can you do that, right? Suppose you have a set of changes that people are arguing should go into the next hard fork. Can you partition them in a way that optimizes something where you say, all right, this next fork, we only want to keep things very safe and do some high stakes changes and move everything else to the next fork. So this kind of discussion right now is super contentious and people argue all the time. Can we actually codify it and make it better? Can we run some simulations and say, hey, by this optimality criteria, you should partition this set of features into these two hard forks. But if these are the criteria, then you can combine them in one hard fork, right? Even big macro questions like, should we design Ethereum for 30 years or 100 years or 1,000 years? If you wanted to ossify, by which is usually meant that you don't make any more changes to the L1 protocol, should that ossification schedule be 10 years or 100 years, right? So this is like a geological strata settling problem. Maybe geologists can tell us something about how to model it. And how do you decide if a feature should be enshrined, by which is meant usually putting it in L1 in the core protocol, as opposed to just leave it at L2s or higher levels. So these are Ethereum specific questions we might be interested in. But the thing about formalization is the motivating practical questions often are only kind of like a stepping stone into what I think of as latent foundational questions, because the big payoff is you can go from these apparently practical questions to really profound questions that open up vast new areas of knowledge and new things you can invent, right? So what would be like a good, I can't think of a good example off the top of my head. Oh yeah, X-rays. X-rays are a good example. It was just Rontgen had some film lying around next to some radioactive material, and the film got exposed and he discovered X-rays, right? This was a very practical accidental discovery, and then it opened up entire vast realms of high energy physics on the theory side, and of course medical applications on the practical side. So there's a lot that can happen if you work on latent foundational questions. So we can ask questions like, is this protocol computable? Is this Turing complete? This is actually a distinction between Bitcoin and Ethereum. So Ethereum is Turing complete, Bitcoin is not. Can you actually simulate this protocol faster than real time? So for example, if somebody makes a huge important change proposal for TCP/IP and the internet will be transformed by it, can you actually simulate it fast enough to see how it operates? Or would it be the case that the fastest way to figure out what it does is to actually do it, right? So that's one way to think of it. What's the fundamental unit of analysis? So this is what Timber and I were riffing on earlier. Should you model the actions of pilots and UAVs, or should you model entire missions, right? How do you represent it? How expressive is the representation? So these are all latent foundational questions you can ask. Finally, I want to give you a little bit of a taste of the kinds of formalization attacks we might consider. Lots of things will be familiar to the technical amongst you. You can use automata theory, Markov decision processes, Petri nets, classical planning and scheduling from good old-fashioned AI. I mentioned temporal interval calculus and region connection calculus. Game theory by itself won't work, but I think certain extensions of game theory might work. I want to point out one that has stuck in my mind for almost 25 years, which is Witzenhausen team theory is kind of the phrase I use for it, which I collected a whole bunch of papers from a course I audited. I'll show you what I'm talking about here. Sorry, not this. So if you search for Hans Witzenhausen in Google Scholar, you'll find a lot of papers. He was a Bell Labs famous researcher in the 1960s. Amazing guy, and he pioneered a whole field. This book is kind of useful. Let's see. This book is worth at least getting a sense of where I'm coming from to this subject. But this is, if you Google team theory with this name Tenekatsis, Tenekatsis is a professor at the University of Michigan. I audited a course from him, and he's the one who exposed me to team theory in Witzenhausen. This is a really powerful formalism, extremely general that, sorry, I'm sharing the wrong tab. So Tenekatsis team theory, very powerful formalism that can model a large range of systems. Some of the work I did in my postdoc was a little bit inspired by this, though not quite following this. But yeah, so there's lots of existing stuff you can draw on. This is what I know about. I'm hoping people can join this conversation who'll expose all of us to other approaches that we might take. But there's a lot here. I mean, this is very tough modeling work, but it can be done. All right, I'm about 6 minutes over. So I do want to say a couple more things. We might come up with completely novel formalizations. So I would recommend looking at Josh Stark's work on hardness, which feels almost like the foundation of something new like information theory. And I'm really intrigued by what can be done with ZK snarks, which is privacy-oriented technology and cryptography system. But I think it might have ways to model protocols in general with privacy and permission-first approach. And of course, AI is changing everything. So we should think about can you use AI to do protocol formalism? I don't know. And there's a null hypothesis here, which is maybe we'll fail. Maybe there is no such thing as a grand unified theory of protocols, and maybe it's not even as formalizable as economics. It's more like, say, anthropology, and that's good. That's good to find out. We should find out what the limits are. Maybe we can come up with the equivalent of Gödel's incompleteness theorems and say, because of such and such characteristics of the way this basket of protocols works, it is impossible to come up with a single formalism that accounts for this stuff. Maybe we'll run into such impossibility results. That would be good too. So that's it for where we are. Take a couple more minutes. So yeah, that's where we are. And this Friday at 10 o'clock, so 10 a.m. Pacific, if you're on the Discord, I will hang out in the voice channel on the Discord, and even if nobody shows up, I'll pull up some papers, start browsing, making notes. But if people show up, we can start chatting and think about what to do. So I'm calling this a warm-up session, but we'll go start moving properly June 27th session, by which I'll have a better idea of how to run this. But if you're interested, just show up on the Discord, show up on Friday at 10, and we'll get going. And also, please fill out the form with your interest in special interest groups, because I will need your email to coordinate this stuff, send out pre-readings and reminders and so forth. And also, indicate your interest in the other special interest groups. Oh, sorry, I'm not even showing the right thing. Okay, so this is back to the overall framework. Yeah, so warm-up session 10 a.m. On Discord on Friday, and then we'll meet every couple of weeks after that and see how far we can get. So that's it, and we won't have time for questions, but yeah, maybe some thoughts from Timber. What do you think of this? Is this a good way to set up our track?
Yeah, I'm really excited to see this one to come together. I don't have the mathematical chops, which is why I'm opting for the more pseudoscientific macro theories, but this will be good to see come together. And I think too, like Seth pointed out, that building intuitions about how to solve these problems is like one very useful component of it. And also just because people are good at building these like deep dive technical models for how to figure out problems in Ethereum and hand washing probably, and like the thing that you showed about modeling like war game scenarios. But yeah, really trying to come up with something that allows people to go into different situations and model protocols in a new way is going to be important. And then the last thing I wanted to touch on is like, I agree that there's not another field that's doing this. I don't think economics is set up to study protocols in this way. I don't think that cybernetics is, and I don't think that typical process theory is either, because it's a very like specific component about protocols. It's like relationship between two organizations and like how they communicate, because it's not like quite info theory, but it's closer to that. It's like a blend of information theory and process theory that I think needs its own just fresh start to model correctly, because you could pick some starting point as an analogy, but I think you're getting off on the wrong foot. So it's better to take like a true swing at it.
Yeah. And I want to point out something, like a lot of people have like, I think, unnecessary math anxiety. And I think people, even with high school level of maths, can do more than they think. And this is why I was mentioning the street fighting math and rough and quick and dirty type math approaches, because I think rigor does not look like extreme jargon and precision. Rigor is almost a state of mind about how carefully you're arguing at a qualitative level. And formalization is not really about, how much math you know, but how kind of like structured your thinking is or can be. Like if you're playing with Lego models, you're doing mechanics in a very formalized, protocolized way, and you're doing it with no math at all, right? A kid doing Lego model building is, in a sense, learning to do formal physical construction in a formalized way. So I do want to encourage people who think that they don't have the math chops to handle this to join our study group anyway and take a stab at this, because I've often seen, by the way, that often the people who do the most profoundly interesting formal theoretical work and profound mathematical results, they're not actually the best mathematicians or detailed formalists themselves. They have like real boldness in how they like frame stuff, how they go after it. And they usually are really good at this street fighting math kind of attitude. Like, they get the big things roughly right. And then other people might be much better at working out the details, but they really kind of like get the direction roughly right really well. So yeah, I want to encourage people who are like even math curious and interested to join us. And one limiting factor will be, I am super rusty. Like, even though I have a PhD in a very mathy field from 25 years ago, I am nowhere near that skill level now. I couldn't do like high school level of like integration and differentiation now easily, I think. So my skills have like half-life of, I think, 10 years. So I'm like 25% of my skill level in 2005. So this is going to be skill limited by my own abilities. Hopefully other people can go much deeper. But yeah, we want to keep it at, say, high school and undergrad, freshman, sophomore level math, and see how far we can get with that. And even if we read very difficult papers that use advanced math, we have ChatGPT now. We can just dump a paper into ChatGPT and ask it, explain this to us in high school math level, right? So
yeah. The other thing I want to touch on, which is good and kind of reflected by that street fighting math like title, which is so great, is for protocols, not making this like a theory initially for just computer scientists, or like it's for everybody to use. So if you like think of it more as like, yeah, street fighting protocol math than anything else, like that's the right kind of caliber to aim for. Okay.
Right. So I think we're hopefully off to a good start. And again, reminder, Friday at 10 a.m. Pacific time, show up and let's start having fun with this stuff.
Yeah, join the Discord if you haven't already. That's where you'll get most of this info, as well as the magazine. And yeah, we'll see you on the Discord, and we're always there, so you can chat with us async. And I'll do the outro now.
Okay. Oh, and remind them of the other 2 study groups. Yep.
Oh yeah. Okay. And we have 2 other study groups, one of which is memory and models for memory, which is led by Kia Kurtler, who recently started her consultancy on memory for organizations. She'll be leading that, I think, about once a month for the next 5 or 6 months. I'll be leading one as well on Spaningsfeld theory, which is about mapping the tension landscapes in organizations, between organizations, in teams, in more complicated, higher level systems like between nations, worrying about security. And these will be going on for 5 to 6 months. So join the Discord, fill out the 6 form. That's where you're going to get more information. And if you give us your email, you'll be included in these. Thanks everybody for tuning in. This is the Protocol Town Hall Guest Talk series. I think next week is still TBD, but we should have more with teachers and engineers and researchers coming soon. And visit the website. It's going through a little rebrand right now, so it might be janky, but lots of good stuff on there. Bye.